This is a semi-classical picture of the lightest atom, hydrogen. An electron describes a circular orbit around the proton. In the lowest energy state, the radius of the orbit is the so-called Bohr radius. This image is inaccurate for several reasons. First, the size of the proton is about 50,000 times smaller than Bohr radius. Second, quantum mechanics teaches us that the electron is not confined to a well-defined orbit, nor can it be located accurately. Instead, it occupies a region of space around the proton, called orbital. This simulation depicts the orbitals as clouds of points. The regions with the highest density of points are those where the electron is most probably found. The ground state orbital is called 1s. The 1 is the principal quantum number, which is related to electron energy. The s means that the orbital quantum number L is equal to 0. S orbitals have spherical symmetry, so the probability of finding the electron does not depend on the direction. The radius of the second Bohr orbit is 4 times the Bohr radius. Therefore, we must zoom out. Quantum level 2 comprises two values of the orbital quantum number. Orbital 2s corresponds to L equals 0. As we see, this orbital occupies a much wider region. Let's make orbital 1s disappear and display only a thin slice of orbital 2s. In this way, we notice a radial node, a distance at which the probability of finding the electron is 0. Again, this is the full 2s orbital. Quantum number L equal 1 gives rise to 3 orbitals called 2p. This is one of them. It consists of 2 lobes which we can consider aligned along the x-axis. The second one, 2py, lies along the y-axis. Finally, this is the 2pz orbital. If we display all 3 orbitals at the same time, the complete electronic cloud becomes somewhat confusing, but shows a high degree of symmetry. The third energy level allows 3 different L's. Again, 3s orbital corresponds to orbital quantum number 0. It has 2 radial nodes. The outer one is clearly visible in this scene. The inner one is hidden by the surrounding cloud. Just as 2p orbitals, 3p ones have dumbbell shape, but with a radial node splitting each lobe. This is 3px. This is 3py. And 3pz. There are several ways to choose the 5 3D orbitals. This is the most popular one. 3 of them have 4 lobes bisecting the coordinate axis. The fourth one has 4 lobes along x and y axes. Finally, the fifth one has two lobes along the z-axis and a ring-shaped region on the xy plane. As quantum numbers grow, the orbitals become increasingly complex in shape, with new lobes and nodes. For example, this is one of the 7 4f orbitals. This is one another. The average electron-nucleus distance also becomes higher and higher. Notice the difference in size with the ground state 1s orbital.